Okay, this is differentiation packet 26B, and in this video we'll be doing a couple of questions from the last pages. We'll be doing numbers 9, 12, and 14. And all of these are looking at a limit question, a limit of a rational function, and can I evaluate it as it is? Do I need to use L'Hopital's rule? And if I need to use L'Hopital's rule, do the conditions for L'Hopital's rule exist? So number 9, the first thing is, can I just plug in 1, right? That's the easiest, and when I plug in 1 to the top, I get 1 minus 1, and on the bottom 1 minus 1, so that's 0 over 0, so I can't just plug it in. That does tell me, however, that condition number 1 has been met. If I plug in my number, I get 0 over 0, so that's a good thing if I want to use L'Hopital's rule. The second condition is, can I take the derivative of the top function and the derivative of the bottom? Yes, I can. The top one, we've got a cube root, which is really a power rule, and on the bottom we've got a linear function, so yes. The third rule is, would the bottom's derivative be 0? Well, the derivative of x minus 1 is 1, so no, it wouldn't be 0, which means yes, condition 3 is met. I hope that makes sense. So all 3 conditions for L'Hopital's rule are met, and that tells me that I can take the limit of the derivative of each part. So the derivative of the top, well, the top is x to the 1/3, so that's going to be 1/3 x to the negative 2/3. The minus 1 goes away, and the bottom will be, the bottom's derivative is just a 1. So that means I can clean it up a little bit, just picky, times the cube root of x to the 2. And now I'm going to plug in the 1. So 1 over 3 times the cube root of 1 squared is just 1/3. So I've found my limit by using L'Hopital's rule after confirming that all 3 apply. And certainly you could check that graphically. Okay, so now we're going to move on to number 12. So in number 12, again, I've got another limit, and I want to take this limit as x approaches 0. So the first thing is, can I plug in 0? And when I plug in 0, I get 1 over 0 squared. So I can't do that, right? But that does tell me that L'Hopital's rule cannot be used. And that's because the first requirement of L'Hopital's rule is that you get 0 over 0. I don't get 0 over 0, I get 1 over 0. So that can't happen. Okay, so we go back to our sort of limit strategies from the earlier part of the year. What can I do when I cannot plug in the number? I could try and factor. That doesn't work here. There's nothing really to factor out. I could graph it. Certainly you could do that on your calculator. I'm going to look at the limit from both sides, because I know that if the limit from the left equals the limit from the right, then the limit exists, right? If these things are true, then we know the limit as x goes to 0 exists. All right, so I'm going to look at what's the limit as x goes to 0 from the left, and what's the limit as x goes to 0 from the right. So I'm going to try and plug in something like that. So this might be something like negative 0.01 squared, and this would be something like positive 0.01 squared. So that's going to be 1 over a positive small number, which leads me to think that it's positive infinity. And this is going to be 1 over, again, a positive small number, which leads me to positive infinity. So I think that, in fact, my limit is positive infinity. And if you graph it, you should see something like this. And in that case, we would get positive infinity. Okay, so there, L'Hopital's rule cannot be applied, but we can still find the limit, kind of using our previous strategies. The last question is going to be number 14, so we'll do that on the next slide. So number 14 is asking for a one-sided limit. Again, we can consider would L'Hopital's rule apply here, and what we need to know. You might want to flip back in your packet to, there was a little footnote on L'Hopital's rule that says, when L'Hopital's rule is being used for one-sided limits, if we reach a point where one of the derivatives, either the derivative of the top or the bottom, approaches 0 and the other does not, then the limit in question is 0 if the numerator is 0, or plus or minus infinity if the denominator is 0. Okay, so we look at this. We can't plug in 0 or even 0 positive, like a small 0 number, because sine of 0 is 0 and 0 cubed is 0. But that tells me condition 1 is met. I would get 0 over 0. Condition 2, can I take the derivative? Sure. Sine of x we know, and x cubed, that's a power rule. So, yep. And number 3, the derivative of the denominator, well, that would be 3x squared. 3x squared is not 0. So, yes, the denominator is okay. So that means I'm going to take the derivative of the denominator, of the whole thing. So we're going to say that this is the same as the one-sided limit of the derivative of sine is cosine, and the derivative here is 3x squared. Okay, so now we're going to basically plug in numbers that are very small but on the positive side of 0. And when I do that, we know cosine of 0 from both the positive and negative side is 1. And if I essentially plug in 0 on the bottom, this will approach 0, right? 3 times 0 squared. And so we would normally think, well, I'm in trouble. But again, if you go back to the note, it says, if one of the derivatives approaches 0, and one does for me, the denominator approaches 0, well, if the denominator is approaching 0, then the limit is going to be either positive or negative infinity. In my case, it's going to be positive infinity because this one is a positive. Okay, and in fact, if you graph sine of x over x cubed, it actually looks a lot like the previous question. It looks a lot like this. So from the positive side, we can see we're going towards positive infinity. Okay, so that's how we can use L'Hopital's rule for a one-sided limit. So I hope that helps. Enjoy.